I will present the paper. So it is a personalized federated learning for the heterogeneous
I think you haven't full screen, so we can still like see the all the other part of the slides.
Oh. Yes, can you see the
yes, it's right now.
Screen? Yeah, okay. Okay, hello everyone. Today I will present this paper on the personalized federated learning for the heterogeneous client with the cluster knowledge transfer. And this paper was just published 2 weeks ago, and all the answers come from the CMU. And from the title, we can find this paper proposed a personalized federated learning algorithm for the heterogeneous client setting using the clustered knowledge transfer method. And this is the content will be covered in today's presentation. And so let's go to the background. So as we know, federated learning enables the thousands of the resource-constrained clients collaboratively training a model without sharing the raw data from the clients to the central server. And currently, most of the federated learning algorithms, for example, the Fed average only trains a single model for all the clients. And this faces a lot of problems when the client hold the heterogeneous data. And here is one example. For example, consider the next word prediction task, and we have several users and hold some local data. And if we have a test sentences, for example, I was born in, so I think, and the correct answer should be some city or some regions. And now if we use the Fed average, and such algorithm will result the same models, and hence if we use this same model for all the users, and they will obtain the same prediction. But here we hope this model can have the different predictions, and definitely in this situation we will obtain a very bad test accuracy performance. So data heterogeneity brings the difficulties to the federated learning. And a way to solve this problem is the personalized federated learning. So personalized federated learning, which aims to train a model for each individual user that can perform well. And there are already some works along this direction. For example, in this paper, model agnostic meta-learning approach for the personalized federated learning. And in this paper, the answer chooses a meta model under the collaboration of the users. And in the test stage, this meta model is updated using the user's local data to get their personalized local models. And in this paper, so the answer use the add additional Morris envelope regularization term, so it is this one, to the local loss functions, and by minimizing this loss function will result different personalized local models for each user. And here in this paper, the answer is using the global objective function in the regularizer. So and it is used to train the individual models for each user. So all these previous works, although they already done some works in the personalized federated learning, but there are already some shortcomings. So the first thing is all these works do not consider the computation and the memory capability of the clients. And as we know, the clients in the federated learning mostly are resource-constrained devices, such as the IoT devices and the mobile phones, and the resource such as computation and memory is important to the clients. And the second thing is the communication cost. And as we know, the modern machine learning models always has larger sizes, and transferring the higher dimensional model parameters between the users and the servers will cost a lot of communication resources. And besides, most of works assume each class model must have the same architecture, otherwise they cannot complete the model parameter average part. So with these shortcomings, and in this paper, the author tried to propose a personalized federated learning framework using the clustered co-distillation to address these previous mentioned shortcomings. So before we go in deep, let me first introduce what is the co-distillation. So as we know, knowledge distillation, it is a knowledge transfer method, and it was proposed to transfer the knowledge from a large pre-trained model to a smaller one, such that this smaller model can be deployed on the resource-constrained devices. And the co-distillation, it is an extension of the knowledge distillation. It enables the distributed training across the different clients. And in co-distillation, only the prediction score or the common unlabeled data set will be shared during the training stage, and there is no model parameter will be shared in the co-distillation. In co-distillation algorithm, an additional regularization term will be added to the local loss function. And such regularization functions forces each client give their prediction towards the averaged prediction result of the all clients of the common unlabeled data set. And we can find, similarly with the previous mentioned Fed average algorithm, if we apply the co-distillation naively to the data heterogeneity federated learning setting, it will force all the clients have the same prediction result, such that it will have have a best accuracy of the data heterogeneity setting. And in this paper, the answer proposed the clustered knowledge distillation framework for the data heterogeneity federated learning. So similarly, it's very similar with the co-distillation. And only the prediction score will be shared. However, the loss function have a different regularization term. And in this framework, each client uses the averaged prediction of only the clients that have the similar data distributions. Before we go in deep to introduce their algorithm details, let me first introduce the basic math notations used in this paper. So we assume we have k clients and they are connected by a central server. And the learning task is an n-class classification task. And each client has a local data, training data bk, and the size of the local training data set is the mk. We denote this pk as the fraction of the local data set for this client K. And the data sample, this psi is a pair of the X and the Y. Here, X is a d-dimensional vector and Y is just a label. And the standard Federated learning loss function is defined as the weighted average of the local loss functions. And this local loss function is defined as the loss over all the local training data set. So now we can continue with the framework proposed in this paper. So let P denote the unlabeled public data set, and we also refer it as the reference data set. And we use SWKX represent the prediction score. So it is the local model WK's prediction score or for this entry X. And the key part in this framework, it is their local loss function. So it is defined as these two parts. This is the conventional mini batch loss or the local training data set. And here, this is the second one. It is the regularization term. So it is a L2 long distance which measures this term sk hat and with this s. So here, this sk hat, it is the average the weight. It is the weighted average the logits from all the clients, and we can find here it has the weight. It is alpha ik, and alpha ik can be the arbitrary set of the weight for the client k. So minimizing this loss function with this regularization term will forces the prediction result of the local model WK moves forward from S to this destination SK hat. So okay, we need to pay attention to this SK here because this index K implies the users or the different client may have the different SK hat here. And if we set this SK hat the same across all the clients, and this time this regularization term will be turned to the Morris envelope regularization. And if we more specifically, if we set this alpha equals 1 over the k, and then this time this local loss function will be degraded to the co-distillation. And in this paper, the answer is using the same clustering algorithm to determine this SK hat. And this same algorithm, in fact, it is the k-mean clustering algorithm we always use in the conventional machine learning field. And here they just use this same to avoid the confusion because we use a lot of k here. And here this SK in the step t plus 1, so it is a stacked logits of the data entry for the public data set. So it is a p by n matrix, and we use this same clustering algorithm obtain the centroid of this of the SK, and finally we will choose the one the centroid which has the minimum distance to the current client's prediction logics. So we will set this centroid. So by solving this, we will using the centroids that has the minimum distance with our logics as this SK hat. So by doing so, we can find the client which have the similar logics distribution will use the same centroid as the SK hat here, and we can further find so the clients which have the similar data distribution will use the same regularization term here, and that means only the client which have the similar data distribution will share the knowledge, and this will yield the better personalized performance. So in this paper, they also provide a toy example to show the effectiveness of their proposed method. So here they consider a simple linear regression task, and the input data is a two-dimensional vector, and so this two dimension is the input, and y is the output, and this color plane is the models. So the different colors represent the different models, and we can find in this graph these answers specific design the model, the true model 0 and the true model 1. They have this, they are very close, while the true model 2 is far away from the true model 1 and the true model 0. And this pink play is the global model that obtained from the Fed average. We can find this Fed average is far away from these two, these three true models, and the right three figures is the result they obtained using the proposed algorithm with or without cluster. So we can find with the cluster, the result model is very close to this true model, and without the cluster, the result model is far away from the true models. This implies the effectiveness of their proposed algorithms. So now we can go through the overall algorithms. So in this paper, the answers also consider the client sample, and here this M is the number of the select clients in this in each round, and here we also define the mini bench size B and B hat for the private and the public data set, and we also define the number of the clusters used in the K-mean algorithm. So we first initialize the score, the stacked score logics, and select the M clients as the candidate clients. And for each communication round, the server will first do a K-mean clustering. So they will obtain the centroids for each cluster, and then select M clients without the replacement from the from all the clients pool, and then send the centroid to each selected clients. And for
I have a quick question here. So if my understanding is correctly, the centroid are used to do the clustering, right?
Yes.
So do they exactly choose the K users for each cluster? I mean, those clustering is kind of orthogonal to each other. That means the one user belongs to cluster 1, it cannot belong to cluster 2, cluster 3, cluster, and the rest of cluster. Is that orthogonal?
Okay. So here, in each round, so they will first sample this. In each round, the global server will collect the scores that from the selected clients, and then they use these clients do a k-mean clustering and obtain these centroids. So this SK is only the only includes those selected clients, and for those not selected clients, they will not considered here. And this centroid is obtained from by do the same k-mean clustering for this M clients. So after we obtain these centroids, and we will send this centroid to we will select another M clients and send these centroids to these clients. So each client only knows the centroids because this centroid is obtained in the server side, and only the centroid will be sent to the clients. So the clients do not know the other clients' prediction logics.
Okay, thank you.
Okay. Okay. So in each client, so they will first get the score, this SK, from the current local model WK, and find the centroid which has the minimum distance with the current score, and set it as the SK hat, and this SK hat will be used to in the local loss function, and to update the local model in further tau local iterations. And after this tau local iterations, the client will do the inference using the updated local model or the public unlabeled data set, and then return this score back to the server.
I have a quick follow-up question. So the centroid is determined by the centralized server, right?
Yes.
So, and the decision of sending a centroid to client K is also determined by the server.
Yes.
But yeah, if you rely on the previous updates, right? Definitely the server can do the centroid, they can divide the whole thing, the whole participants into several clusters, and sending the centroid to corresponding clients. Excuse me. For example, cluster K in clients K in cluster 1 or in cluster 2. It's reasonable, but is it depends on current updates of the clients, or depends on previous updates of the client? Previous round of updates of the client. I mean, if you consider line 11 and line 12, right? So
the server can determine this, but here we have this client sampling. That means for the new selected clients, they may not join the previous communication round. So this is why they need to send all the centroid to the client key, because they need to make sure every client, every selected client, they have this SK here.
So here's they send all the centroids to cluster to client K.
Yes, and the client K will select one, select one from the centroids, and as this SK hat.
Well, it seems it's not. If you consider the second line of number 11, index 11, it seems the client K, it has a vector, and it's going to calculate all the vector of centroids with its own vector somehow, L2 norms, and minimize that, and pick up.
Yes.
Oh.
Okay. Yeah. This is.
Gotcha. Yeah. Okay. Thank you.
Okay. Okay. So any problems? Okay. So if not, I will continue. So in this paper, the answers also provide the theoretical convergence analysis guarantee of this proposed algorithm, and they also provide the theoretical grounds for the generalization performance. And they prove that under the local Lipschitz condition, and the norm of this SK hat will go to 0 with the probability 1 as the communication round and iteration go to the infinity. And they also provide the proof for the generalization probability bound. Okay, and but for this mathematics thing, I think it is out of today's scope, so I will skip it. Okay, so let's go to the experiment part. So okay, in this paper they use the training and the test data set is from the CIFAR 10, and so this is a 10 class classification task, and the public data set is selected from the CIFAR 100 data set, and they randomly sample 2,000 unlabeled samples from the CIFAR 100, and the number of the clients, so it is 100, and the client sampling fraction, so they consider the two fractions, the 10% and the 50%, and they consider the two scenarios, and the first one is the model homogeneity. That means all the clients have the same model architecture, and in this time, every client deploy a VGG11 model, and the second scenario, it is a model heterogeneity scenario. In this time, each client will randomly sample one model from VGG11, VGG30, and CNN. And the data distribution, they use the Dirichlet distribution to split this CIFAR 10 data set, and the alpha of their Dirichlet distribution equals 0.01. And this is a graph. The graph shows the label distribution over the clients. We can find this is a highly non-ID distribution. And in the experiment part, they consider several baselines, which includes the Fed average, Fed prox, and Fed formal and detail, and all these methods. This method is a very famous algorithm. So this is their result. So in this table, they show the test accuracy with the communication cost under the model homogeneous scenario. And we can find this fat formal achieves the best test accuracy, and their method achieve the second best, but we can find the communication cost is much less than this fat formal. And for the Clyde sample duration equals 50%, the result is the same. And this is the result for the model heterogeneity scenario. And we can find here their method also achieve the state-of-art test accuracies under these two settings. And their communication cost is much smaller than the other than the previous algorithms. So, okay, this is all today's presentation. Any problems?